In public health, we live by the numbers. They're supposed to give us the hard facts. But what if I told you that sometimes those numbers, they lie? Or at least they don't tell the whole story. We're always comparing data, right? Trying to figure out what's really going on. But there's a huge trap. If you're not careful, you end up comparing apples to oranges, and the conclusions you draw could be totally wrong. Okay, let me set up a little mystery for you. Let's say we've got two cities. We'll call them City A and City B. And the question is simple. Which one's less healthy? Seems like a no-brainer, right? Just pull up the stats and you've got your answer. All right, so we look at what's called the crude death rate. That's just the total deaths for every 1,000 people. And what we see is that City A has a rate of 6.6, but City B, its rate is 7.3. So looking at that, you'd think, wow, City B is clearly the less healthy place. Case closed, right? Well, not so fast. Because here's the twist. What if City A is basically a giant retirement community, packed with older folks, and City B is this young, vibrant college town? It makes sense that an older population is going to have a higher death rate, even if they have the best healthcare in the world. That age difference, that's what we call a confounding variable. It's a sneaky factor that gets in the way and completely messes up our comparison, hiding what's really going on. So how in the world do we fix this? How do we untangle this mess to make a fair comparison? Well, thankfully, we have a tool for exactly this problem. It's a process called standardization. You'll also hear it called adjustment, and it is designed to slice right through this kind of confusion. And really, the idea behind it is pretty straightforward. Standardization is all about mathematically erasing the effect of a distracting factor, like age. It's like we're leveling the playing field so we can finally see what's really happening underneath it all. Think about it. Comparing that retirement community to a college town, that is the definition of comparing apples and oranges. What standardization does is, well, it's the magic that turns them both into apples. It lets us get a real, honest look at which city actually has the higher death rate, once we've taken age completely out of the picture. Okay, so you're probably wondering, how do we actually do this? Well, there are two main ways to go about it, two main methods. You've got the direct method and the indirect method, and which one you use really depends on the situation. Let's break them down. The big decider here is your data. If you've got super detailed, reliable death rates for every single age group in both cities, awesome. You'll use the direct method. But what if your data is a bit spotty? Or maybe you're looking at a really small group where the numbers would be all over the place. That's when you turn to the indirect method. They each ask a slightly different question, but trust me, they're both incredibly powerful. So the direct method, it's all about asking a what-if question. It basically says, okay, let's take the real actual death rates from City A and City B, and let's apply them to one single standard population that we all agree on. By forcing them to have the exact same age structure, any difference we see at the end, well, it can't be due to age anymore. We've eliminated it. The process is pretty logical. First, you choose that standard population. It could be something like the entire country's population structure. Then, for each city, you use their own age-specific death rates to figure out how many deaths you would expect to see in that standard population. And once you have that, you just calculate the new adjusted rate. And boom, you've got a number that's actually fair to compare. All right, now let's flip over to the indirect method. This one kind of flips the whole question on its head. Instead of creating a pretend population, it creates a pretend number of deaths. It asks a different what if. What if our small specific group, let's say a community of minors, had the exact same death rates as the general public? How many deaths would we expect to find? This approach is a lifesaver when your data is thin. I mean, think about it. You can't get reliable death rates for every age group when you're only looking at, say, 200 minors. It's just not enough data. So instead, you do something clever. You compare the number of deaths you actually saw in that group to the number you expected to see. And that comparison gives you this really powerful metric called the Standardized Mortality Ratio, or SMR for short. So let's stick with that mining community example. Imagine we crunch the numbers and we get an SMR of 150, just a single number. So what? What does that even mean? Well, here's how it works. An SMR of 100 means everything is normal. The death rate is exactly what you'd expect. So an SMR of 150, Whoa, that is a huge red flag. It's telling you loud and clear that the death rate in this community is 50% higher than it should be. That's a massive signal that something, maybe an occupational hazard, is terribly wrong and needs to be investigated right now. This isn't just a statistic, it's a number that can quite literally save lives. And this stuff isn't just some abstract academic exercise. No way. Standardization is used every single day in some really high-stakes situations where making a fair comparison can literally be the difference between life and death. I mean, think about it. When the World Health Organization needs to compare cancer rates between a country like Japan, with a very old population, and Nigeria, with a very young one, how do they do it fairly? Age standardization. When scientists needed to prove just how dangerous asbestos was, what did they use? SMRs, to show those workers were dying at shockingly high rates. It's used all the time in national health reports, and even to compare the performance of different hospitals. Okay, so now that we know all this, now that we have this powerful tool in our back pocket, let's circle all the way back to the beginning. Let's solve that mystery of City A versus City B. Now, if you remember, just looking at the raw numbers, the crude rates, City A was at 6.6 deaths per thousand, and City B was at 7.3. It really looked like City B had a problem. But we know now that was the illusion, right? That was the whole apples and oranges trap. But that was just the illusion. So, here's the reality. Once we use direct standardization and adjust for those age differences, look what happens. City A's rate is now 6.4, and City B's is 7.1. So yes, City B still has a slightly higher rate, but look at how much that gap has closed. It's way smaller now. It turns out a huge chunk of that original difference had absolutely nothing to do with health. It was just demographics. Standardization let us pull those two things apart and finally see the real story. And, at the end of the day, this is so much bigger than just a math problem. This gets to the very heart of the ethics of public health. Because if we make unfair comparisons, we could end up sending resources to the wrong places or unfairly stigmatizing a community and just completely missing the real problem we're supposed to be solving. Standardization isn't just a technical fix. It's a promise. It's a commitment to being fair. It's how we make sure that when we say one group has a higher risk, we know it's a real health issue, and not just because they're older or have a different gender balance or some other quirk in their population. Because ultimately, if we want to make good decisions that actually reflect reality, it all comes down to a very simple but profound idea. In public health, fairness begins with how we count.